Welcome to Free Learning Academy. Let's simplify real-time CPU scheduling. Imagine a system where being even a fraction of a second late is not just inconvenient but dangerous. A delay doesn't mean a slower experience, it could mean a system failure, a financial loss, or even risk to human life. This is exactly where real-time CPU scheduling comes into the picture. Unlike the general scheduling algorithms we explored earlier, where the goal was fairness or efficiency, real time scheduling is all about timing guarantees. Here, the operating system must ensure that certain tasks are completed within strict time limits. It is not just about finishing a task, it is about finishing it at the right time. To understand this better, think of a traffic signal system at a busy intersection. The lights must change at precise intervals to keep traffic flowing safely. If the signal delays even slightly during peak hours, chaos can occur. Similarly, in real time systems, tasks are scheduled in such a way that their deadlines are always respected. These tasks are often triggered by events such as a sensor reading or a user action, and the system must respond immediately within a defined time frame. Now, before diving deeper, let's connect this with what we already know about CPU scheduling. Earlier, we discussed algorithms like round robin, SJF, and priority scheduling. These algorithms aim to optimize performance metrics like waiting time or turnaround time. But real time scheduling is different. Here, the focus shifts from how fast to how predictable. Predictability becomes more important than average performance. The system must behave consistently even under heavy load. Real time systems are broadly divided into two categories: hard real time systems and soft real time systems. Let's start with hard real time systems because they represent the strictest form of scheduling. In a hard real time system, missing a deadline is simply not acceptable. It is considered a system failure. These systems are used in environments where timing is critical and errors can have severe consequences. Take the example of an airbag system in a car. When a collision occurs, the system must detect the impact and deploy the airbag within milliseconds. If it is too early or too late, it can fail to protect the passenger. There is no room for delay. This is a classic example of a hard real time system. Similarly, medical devices like pacemakers must deliver electrical pulses at precise intervals. A missed deadline here could directly affect a patient's life. In such systems, the operating system uses highly deterministic scheduling algorithms. Tasks are assigned priorities, and the scheduler ensures that high priority tasks always meet their deadlines. Techniques like rate monotonic scheduling or earliest deadline first are often used. The key idea is that the system is designed in such a way that deadlines are guaranteed under all conditions, assuming the system is properly configured. Now let's shift to soft real-time systems, which are more flexible. In a soft real-time system, deadlines are important, but missing them occasionally is acceptable. The system performance may degrade, but it does not lead to catastrophic failure. These systems are more common in everyday applications where timing matters, but perfection is not required. Think about video streaming. When you watch a movie online, frames must be displayed at a steady rate to ensure smooth playback. If a frame is delayed slightly, you might notice a small lag or drop in quality, but the system continues to function. This is a soft real time system. Another example is online gaming. If the system responds a few milliseconds late, the experience may feel less smooth, but the game does not crash. The key difference between hard and soft real time systems lies in how they handle deadlines. In hard real time systems, deadlines are absolute. In soft real time systems, deadlines are more like targets. Missing them occasionally is tolerated, as long as overall performance remains acceptable. Let's take a simple comparison to make this clearer. Imagine you are taking an exam. If the rule says you must submit your paper exactly at 10 a.m., not a second later, that is like a hard real time system. Missing the deadline means failure. On the other hand, if the teacher allows a small grace period, say a few extra minutes, that resembles a soft real time system. The deadline still matters, but there is some flexibility. Now, How does the CPU scheduler actually manage these real-time tasks? In real-time scheduling, tasks are often periodic or event-driven. Periodic tasks occur at regular intervals, like reading sensor data every 10 milliseconds. Event-driven tasks occur when something happens, like a button press or a system interrupt. The scheduler must ensure that all these tasks are executed within their deadlines. To achieve this, the system may use preemptive scheduling, where a currently running task can be interrupted if a higher priority task arrives. This is similar to what we discussed earlier in preemptive scheduling, but here the stakes are higher. The scheduler must make quick decisions to ensure that no critical task is delayed. Another important concept in real-time scheduling is latency, which refers to the delay between an event and the system's response. In real-time systems, minimizing latency is crucial. The operating system is often designed to reduce overhead, avoid unnecessary delays, and respond to interrupts as quickly as possible. It is also worth noting that real-time systems are often used in embedded environments. These are systems with specific functions, such as industrial machines, robotics, or automotive control systems. In such environments, the operating system is lightweight and optimized for predictable behavior rather than general purpose computing. Now, if we connect this topic back to the earlier discussion on types of operating systems, real time operating systems were already introduced briefly. What we are doing now is diving deeper into how scheduling works inside those systems. Unlike general purpose OS, where multitasking and user experience are the focus, real time OS is built around strict timing requirements. As we move forward, you will notice that real time scheduling also connects with other topics like interrupts, synchronization, and even deadlocks. For example, if a high priority task is waiting for a resource held by a low priority task, it can lead to priority inversion, which must be handled carefully in real time systems. In the end, real time CPU scheduling is all about trust. The system must be trusted to respond within a guaranteed time frame. Whether it is controlling an aircraft, managing a robotic arm, or simply streaming a video, the scheduler plays a crucial role in deciding how and when tasks are executed. And understanding the difference between hard and soft real time systems helps us see how operating systems are designed to meet very different kinds of requirements, from life critical precision to everyday responsiveness. That is it for this video. See you in the next one.